So, hi, my name is Ayan Salisora, and this is my video explanation for task 8.1. This task contains 5 parts, all related to graph algorithms and their applications in real-world scenarios like hotel navigation, network connectivity, and route planning. I'll walk you through each part and try to explain the logic and code and also the time complexity and correctness for each solution. So yeah, let's get started. So we'll start with part A, which is to like calculate maximum number of shortest paths using BFS, which is breadth first search. So yeah, so here we are given an unweighted graph, which is GVE, and like so GVE is like a city map and a source node S, a source node S to uh, so this is a good uh, we can say like a uh, starting hotel. Okay, so we can say this as a starting hotel, and the task is to compute the number of shortest path from S to every node. Okay, so yeah, so because uh, BFS explores in layers, meaning it visits all nodes at distance 1 first, then distance 2, and so on. This is a perfect for unweighted graphs because the first time you reach a node, it's where the shortest possible path. So yeah, so let's go through pseudocode. Before that, the distance v is the shortest distance from S to V, and count v is number of short paths from S to V. And we initialize distance S is equals to 0 and count S is equals to 1 as BFS explores, and if a shorter path is found, we'll update distance V, and if another shortest path is found, we'll increment the count V. So yeah, let's go through our pseudocode real quick. So we'll start with the for loop for vertex V in graph. So the distance V is equals to infinity. This initially assumes all the nodes are unreachable, and count V is equals to 0. This uh, this means that there are no paths known yet, and distance S is equals to 0. This tells us that the source node is 0. Source node is 0 distance from itself, and the count is equals to 1, which states that there is one path from S to S, trivial path, like a trivial path. So Q is empty Q. And then we have a while loop Q. So while loop for Q is not empty. So here U is DQ. So we are using this to explore from the front of the queue, and we start a for loop here inside a while loop for each neighbor v of u. So if distance v is equals to infinity, the first that means this the first time seeing node v. So this is so the distance v is equals to infinity here in this line means the first time seeing of node v. So distance v is equals to distance u plus 1. This is just setting a distance, and count v is equals to count u is inheriting path count, so it's just copying the count here. And else if distance v is equals to distance u plus I, so we are adding condition for else if. So this means another path is found, and count v plus or is equals to count u means we are adding additional paths. So what's really happening here is, let's say you are at node u, okay? So let's say you are at node u, for example, and you find its neighbor v. So if v hasn't been visited, you record the distance between the distance and path, the count. So if v hasn't been visited, you record the distance and the path count. So if it's already visited at the same distance, it means you found an alternative shortest route. So you increment the count. This allows you to, count all different ways to reach a node using the shortest of the hops. So the time complexity of this is like each node and edge is processed at most once in BFS. So it's O n plus m. So the time complexity is O n plus m, where n is number of nodes and m is number of edges. So yep, so this was our part A, to calculate the maximum number of shortest path to a hotel. Now we'll come to the part B, which is graph connectivity using DFS. So the problem here is we have to check if the graph is connected, meaning all the nodes can be reached from any starting point. So you start from anywhere and it can be reached from any starting point. That's what it means. So yeah, so the reason why we are using DFS, which is depth first search, so is so DFS is easy to implement, and it's effective for exploring all the reachable nodes. That's why we are using the DFS. So yep, so let's go through our pseudocode for this one. So we start off with a function is connected graph, and in that we set visited is equals to set. So this is just keeping a track of visited nodes, and start is equals to any node in graph. Uh, this is just picking an arbitrary node to start, and then we use the DFS uh, with the parameters of graph, start, and visited, and we return the size of visited equals to node number of nodes. So this means if all the things are visited, all the nodes are visited, that means the graph is connected. So then we use the function DFS. We make a function DFS where we use this parameters graph, node, and visited. And here the visited we are using add node for with the visited here, and this is just to mark current node as visited. And we use a for loop for neighbors in graph node. So if neighbor so if uh, so here we are using an if condition here. So if neighbor is not visited, neighbor not in visited, the DFS becomes uh, graph neighbor and visited, which is recursive visit. Let me just charge my laptop. Sorry. Yep, sorry about that. So what's happening in this code is uh, we start at one node, okay, and we are using recursion to visit all the reachable neighbors. And when the DFS finishes, if the visited set has all nodes, the graph is connected. So this is what the code is about. And so you might have like a doubts like, can this detect disconnected graphs? So the answer to that is like yes. If not all nodes are in the visited set, then at least one node was unreachable, indicating the graph is not not connected. So it's disconnected. So the runtime for this is O n plus m, same as the BFS, which uh, which is the same as the earlier one. So this was all for the part B. Now we'll move on to the uh, part C, which is DFS with adjacency matrix. So if DFS is performed on a graph using an adjacency matrix, which is size n by n. So this helps us to find neighbors for each node and checks this makes sure we check all the n columns, and the total work for n nodes is O n square. So O n square is a runtime for this. So yep, let's move on to the part D. So in this part we are just so this part is about Dijkstra's algorithm on adjacency matrix. So here we are given a cost adjacency matrix, which is 10 by 10, representing a directed weighted graph. And the uh, and we have we've been given node labels 1 to 10. So and also the edge weights are given as numbers, means no connection. And we have to use Dijkstra's algorithm from node 1 to find the shortest path to every other node. So that's what we are doing in part D. And the reason why we are using Dijkstra's algorithm is the algorithm is ideal when all the edges edge weights are non-negative, and also when you need the minimum cost path from one node to all others. So Dijkstra's steps, to calculate Dijkstra's steps, conceptually, uh, is to like first is to like initialize distance. So the distance u, so the distance source is equals to 0, and all other are set to infinity. And the second step is to use a priority queue to always set the node with the smallest distance. And the third step is to, for each node removed, we relax its neighbor. If distance u plus cost is less than distance v, we update the distance v. And we also track the pre-array to reconstruct the path tree. So that's the Dijkstra steps to calculate all. So yeah, so the node removal order based on minimum distance is 1 to 2 to 4 to 6 to 7 to 8 to 3 to 5 to 10 to 9. These orders shows how the priority queue always picks the next closest node. So let's break down each node in this shortest path tree. So we have node, 3 columns here, which is first one is the node, second is distance from one, and the third one is previous node. So the node 1 has its distance from 1 is 0, previous node nothing because we just started, so we don't have any previous node here. So this goes like this goes on. So node 1, distance from 1 is 0, and previous node is nothing. So this is a start node, and then we go move on to the second node, uh, whose distance from 1 is 3, and the previous node was 1. So the direct edge is currently 1 to 2, and the third node is 3, and the distance from 1 is 17, and the previous node is 8. So path 1 to 2 to 8 to 3, like that. And the fourth node is 4, whose distance from 1 is 8, and previous node was 2. So the path here is 1 to 2 to 4. So it's 1 to 2 to 4, like that. So the fifth node is 5, whose distance from 1 is 19, and the previous node was 3. So the path here is 1 to 2 to 8 to 3 to 5. Uh, the sixth node is obviously the node 6. The distance from 1 is 9, and the previous node was 4. So the path will be 1 to 2 to 4 to 6. So 1 to 2 to 4 to 6. And node 7's distance from 1 is 10, and the previous node was 2. And the path will be therefore 1 to 2 to 7. And node 8's distance from 1 is 4, previous node 2. That means the path will be 1 to 2 to 8, and the knots the knots nines distance from 1 is 25, and the previous knot was 5. The path therefore is 1 to 2 to 8 to 3 to 5 to 9, and the knot 10 distance from 1 is 22. The previous knot was 5, so the path is 1 to 2 to 8 to 3 to 5 and to 10. So that was the resulting shortest path we calculated based on the uh, uh, you know node removal order. There was our part D. Now let's move on to the part C. Sorry, part E. My bad. And if you like for the part D, if you have like questions like why Dijkstra is better than BFS here. So the reason for that is that Dijkstra's work, Dijkstra works with weighted graph, and BFS assumes all weights are equal. So in this case, edge cost matters, so Dijkstra is needed. And why don't we use DFS here is because DFS doesn't guarantee minimal distances, especially when especially in weighted graphs. It might explore longer paths first. So that's why we don't use DFS here. So the only ideal one is Dijkstra. Now, yep, let's move on to the part E. So this is path validity after weight increase. So the question was, if each edge weight is increased by 1, will the shortest path P from S to T remains the shortest path? So the answer to this is yes, because all the edge weights increase by 1. Any path of k edges becomes weight plus k, w plus k. The relative order of path lengths remains the same, and the p remains the shortest because all the alternative paths increase by the same number of edges. So the shortest path in an edge-weighted graph with all positive weights depends on total weight. So increasing all weights equally per edge keeps the shortest path structure intact. So that was it for part E, and also this was it for the task 8.1p. I hope this video clearly explains each part of the task, the algorithm used, and why they are appropriate. I've also analyzed like the time complexities, explained the shortest path, logic in depth. I've done this work. Uh, it took me quite a time to do this work, and I also validated each step through research and testing. Thank you for watching this video, and yep, so this is the last task, so this is it for the unit, I guess. Alrighty, have a good day or night, whatever.